That's their problem. Yeah. Or yeah, like you. Are you okay with being recorded? Yeah. And on the whole other end. You said. Okay. All right. Hello, everyone. Thanks for coming in. I'm actually, so my name is Ravi Raghunathan. I'm faculty with the Department of Electrical and Computer Engineering. I'm actually filling in this week for Dr. Boker, who had other commitments, so he couldn't be here. So it's my pleasure to introduce Dr. Joseph Kozak, who's one of our own. It's always a pleasure to have our alumni come and do these talks. It's a great experience for you guys as MM students. So Dr. Kozak received his BS and MS degrees in engineering physics and electrical engineering from the University of Pittsburgh, and his PhD degree in electrical engineering from the Center for Power Electronic Systems, so CPES, right here at Virginia Tech. Since 2021, he's been a senior electrical engineer at the JHU APL, which is Johns Hopkins Applied Physics Lab, and is currently serving as chief technologist for the spacecraft power engineering group. So Dr. Kozak primarily supports the NASA Dragonfly project, as well as the Lunar Surface Innovation Consortium, or LZIC, specifically the Surface Power Focus area. He's an active volunteer in both the IEEE as well as the AIAA. So as far as the talk goes, if you've had a chance to look at the abstract, basically the field of power electronics, of course, doesn't need an introduction. It's ubiquitous. It's very useful to pretty much every industry we can think of that has anything to do with power electronics. And it's trending toward designs with higher power densities. Aerospace applications in particular have had difficulties achieving terrestrial metrics due to limitations on reliability and radiation hardened components. So this talk will provide an overview of the design considerations faced in electronic circuits that are used in deep space applications. So examples will include the challenges in designing the most recent NASA New Frontiers program, and Dragonfly in particular, as well as the future lunar power grid. In addition, how facing these engineering difficulties can help shape your local community and the next generation of engineers on Earth will all be part of the talk. So without further ado, let me let Dr. Kozak take over.
Thank you. All right, good afternoon, everyone. So my name is Joseph Kozak. It's a pleasure to be here with everyone. Please, most people call me Joe. So we're here, we're gonna have a conversation. I'm gonna talk about some of the stuff that I'm very nerdy and passionate about. We'll start getting into things. But first, I'd like to introduce myself a little. I was a graduate student as well, as you heard. But before then, I grew up in Lower Merion, Pennsylvania. Went to the same high school as Kobe Bryant. You can see there I am, and I'm here right now, and there's Kobe, and I can't dunk, so it's really a special moment. And as mentioned in the bio, sorry, I put these slides together too without knowing exactly everything. So I moved over to Pittsburgh. You can see the beautiful Cathedral of Learning. It does rival Burris Hall down in Blacksburg. So after spending a good amount of time up there, I moved down to Blacksburg to start a PhD degree at the Center for Power Electronic Systems. And you hopefully all seen the 4th floor and 5th floor labs here, if you don't work in them already. And if you do, God help you. Since then, I left. Somehow they let me go in great fashion. But during my time at Virginia Tech, I also had internships all across the country in North Carolina, Colorado, and California. As a result, one of my fun facts is I've been to the continental 48 states. And then all of that afterwards, I've now started a career at Johns Hopkins Applied Physics Lab. I'm in the spacecraft power engineering group. So from the lab perspective, I'm a senior member of the technical staff. And for my group in particular, I'm the chief technologist. And what does that mean? It means I'm a bigger nerd than most of the other nerds. And I love to learn about what's going on here. So thank you all for talking to me, who I've gotten a chance to today, and learn about what you're doing, what you're working on, and what is the state of the art, and what's the future. So it's really exciting to learn about. Currently, as mentioned, I primarily support the NASA Dragonfly project, which we'll talk a whole lot about, because what's an ECE presentation without some good hardware, pictures, and videos. I'm currently the battery lead, so I don't know anything about batteries, but my education and training as a graduate student has provided a background to be able to learn and adapt. So luckily, staff members have at work have seen that, and they've put me in charge of this 300-pound bomb. I'm sorry, it's not a real thing. It's a 300-pound 100-volt lithium ion battery that's going to be dissipating up to 30 kilowatts of power. So I watch our safety guide very closely during any tests. Additionally, I do support, I'm a member of the rotor drive electronics team as well for Dragonfly. And that's actually what most of the talk will be about. And I serve on the Lunar Surface Innovation Consortium. We run some research and development programs. So at least myself, I haven't left the mindset, because I'm friends with people who are in academia, that I still am a fake academic and want to do everything and be involved. And it's exciting, but you know, I do like sleep. So I'm trying to learn how to do that. So today's talk is going to be a little bit about, with a background. I know a lot of you have great fundamentals in power electronics, but so that we're all on the same basis, we'll have at least one slide on it. And then we'll talk about some of the challenges of, you know, I helped build things for here on Earth for 7 years. Now, how do you take that information, and what are the changes and challenges of trying to build electronics for space, particularly deep space, which it will define as geosynchronous orbit and beyond. So we'll have two examples primarily going into that, Dragonfly and the power grid for the moon. And then I'd like to bring us back and have a conversation of why is that important for us to do? What are the advantages of doing some of this work? And then also even bring it back as we're not just engineers, but we're also people. So starting things off, that's Dragonfly. And the most important thing, despite us trying to build our very particular types of electronics, is what is our application? What are we actually going to be supporting? If you're building communication networks, if you're building mechanical infrastructures, if you're building power supplies, what is that going to be in, and what is that going to be supporting? How are we going to use it? In this case, our systems application is a drone. It's an octocopter that's going to be flying on another planet. So from my background, and actually thank you, because I've stolen some of these graphics from some of our guests here. From the power perspective, you have your system application, and you break it down for power converters themselves into packaged modules, and all the way down to power semiconductors themselves. So my background and dissertation work was primarily on the reliability of power semiconductors, but my whole dissertation committee had individuals at each of these levels to help keep me balanced and understand where the importances are. And below power semiconductors, you have material scientists. And you know, I'm sorry to say they're weird, but they're the real people who can change and shift the paradigm of our technologies. Additionally, there's a lot of additional, what I would say, auxiliary considerations going into creating any power electronics conversion system. So you have your magnetics, you have your thermal management. I'm going to talk a lot about today, some of that. And then you have controls, or the math people. So I'm not as inherently naturally gifted at math, so I got put into being more of a tester and looking at some of the electronics themselves. But from this standpoint, is what I want us to take away from this slide is, even though we are built, or my group, or the team I am a part of is building the power converter, there are many facets that we have to keep into consideration. And as you are going through your graduate studies, you are starting to learn how to go not only think about the vertical integration, but also horizontally. What are the thermal management systems? What is the mechanical infrastructure that I need to have to be able to support my overall system? So taking that, we're going to have a little fun. We'll look at the solar system. Supposedly next year in January, you'll be able to see 7 planets in the sky. That's my fun fact for you. So as I've been learning about how to develop electronics for space applications, there have been a lot of constraints that have been approached and thought of. Whereas before, you know, I can just build my system bigger if I need to keep it cooler. I can increase the airflow. I can increase the number of components I have to distribute current. I can make things a little easier from my perspective by just increasing the size. Well, size and mass are very constrictive. Going to space, you only have so many types of delivery mechanisms. There's only the rockets are only so big. So your payload as your application has to be constrained to a certain size. And any kilogram or gram of mass that you're putting on there is going to cost so much more money to get up there that you have to really consider some of these other external factors. And you might grow too much, so you're even constrained on size, which is one of the problems, at least with Dragonfly. We've been on a diet for about the last year and a half, and it is a challenge. Not only are we thinking about size and mass as some of our design constraints, but we have to think about the interconnection of how these structures are. So for instance, when you launch a rocket, there's a shock event right when you start blasting off, and the whole ride is you're on a roller coaster shaken quite violently. So it's fun to watch these tests, but I've also seen capacitors fly off circuit boards, and you know, one of those things coming at you at whatever speed is not going to feel great. So these are things I've never at least thought of until starting to get into this area of work. So along with that, the environment itself, as someone who works in the aerospace industry, there is a 0% chance I'm going to space. I do not want to deal with these environments. It does not seem fun. But you know, hey, I want to enable everyone else to follow their dreams. So I'm going to help you get there. And with that, from some of the environments for us to consider are one, well, we'll start from the bottom, is a vacuum environment. We're breathing air here. We have a pressurized gas from our atmosphere. Well, once you get into areas of deep space, you lose that. There's no more pressure keeping your system, so you have to think about your systems differently. That also means you're restricted on types of materials you can consider. So we have a big material constraint problem, which I'll get into. But along with those things, so you might have problems with outgassing some of your insulation materials. Going to the temperature profiles, well, it's really hot over here. Oh, hold on, ready? Pointer option, laser pointer. Okay, it's really hot over here by the sun. Well, it gets really cold out here. So one of the biggest things is how can we make sure that our electronics or any of our systems are able to operate given the different fluctuations in temperature. So as someone who's now working on a battery, this is the most sensitive thing I've ever worked on. If it gets a little too cold, it's unhappy. If it gets a little too hot, it's unhappy. You know, this is Goldilocks problem right here. We're trying to say sweet nothings to it all the time. And then, as I kind of alluded to, materials are a huge challenge. So designing anything has various constraints, whether it be going from aluminum to magnesium frames, whether it is what type of epoxy you can use, whether it is what kind of shielding you can utilize to protect you from the sun, like the Parker Solar Probe, which has been going around the sun and has gone within parts of the sun's corona. Don't ask me what that means. I just read it online. But these are different projects that APL has been a part of, as I've mentioned ad nauseum. I'm on Dragonfly, but the most recent one, Europa Clipper, launched with about a month ago. So it's quite exciting. And, you know, I can just tell you now, in about 6 years, then it'll be exciting again because it takes that long to get there. So keeping on some of the environments, I want to kind of go through this a little bit, just so that we have a basis when thinking about some of the other aspects, particularly the lunar grid. So in this case, as thinking about a satellite going around our atmosphere, well, it happens to actually pick up charge as it's going around. So there's a huge grounding problem within all spacecraft. And so there are ways of mitigation on how charging is handled and how do we want to make sure to distribute that throughout. You can get plasma events and you can have plasma form under certain instances as well, which I certainly don't want. One of the areas that I'm very interested in and excited to continue to learn is radiation effects, ionizing and non-ionizing doses, single event effects. These are things that accumulate damage over time. As I mentioned, I did reliability studies on semiconductors. So those are exactly what I'm starting to be interested in studying and learning and understanding more, because you might be switching and operating no problem. Your radio might be transmitting perfectly, and then just out of the blue, a high energy particle hits it, and now you have an interrupt in your FPGA or a microcontroller. Now you got no signal. Well, how do you reset that? Can you reset that? What are the tolerances? So I'm not going to go through all of these. The one that I really kind of find interesting, and I think about it more for solar panels, is micrometeorites and orbital debris. So now that we have a lot more satellites going through space, the decommissioning of all of these satellites and anything that is in our or various orbits of Earth, or even going out into further into deep space, these micrometeoroids can really damage and impact especially the coatings that you have over solar arrays. And so you're starting to lose energy, or your capability to generate energy because of something that's like the size of a pebble. All right, so now is a little bit of a fun. As I said, you guys are welcome to ask questions at any time. To me, that's more fun, but we can have some nice conversation at the end. But otherwise, we'll start jumping in a little bit into the Dragonfly project. And to start, I have a little video. Will they be able to hear it online? All right. Where is, I just want to turn that off. Go. It's that last little ding that gets me every time. Hold on, I have almost the same information on the next slide, so we'll just jump here. So now we have all a little bit of a baseline of what this project is that I'm obviously very passionate about. It's not like they pay my salary and tell me I have to say it. So to me, I came to work at APL partially for this project, and it's because it's developing something that's never been done. And that's one of the things that I've enjoyed particularly about graduate school, is that, you know, you're around people who are trying to solve problems that have never been answered before. Now, you might have made up your own question and problem, which happens quite frequently. But in this case, some really smart people who are far beyond my capabilities have realized that there are places in the solar system that can help us answer questions that we have about the Earth and how it was formed, based off of a moment in time. And to me, as an engineer, that's really exciting to be able to support them answering that question. Well before graduate school, I thought I wanted to be a physicist. I wanted to do high energy physics. And then I realized that it would take 40 years before there might be something that I've done that contributed to the world. And then I realized what being an engineer is like. And I'm like, wow, this is actually cool. I won't be dead before this is important. So with the NASA Dragonfly project, there's a couple really interesting aspects with what's happening. So after we launch and we go through that big kind of impulse event, we're flying through our atmosphere, we finally get into space. Well, at that point, we are in this spacecraft cruise stage and entry vehicle. Let me go back to this pointer option. Here we go. So we're going to be in this cruise stage. We're going to be in this aeroshell. So if you remember that logo at the end, or it's on my laptop, which is hidden, but it's to me, it's the exciting part. And that's what we'll be flying through space. Now, who knows where I'll be working or what I'll be doing after we launch, but as it takes about 7.5 years to get to Saturn. But we're going to get out there, and then we're going to start to descend into the Titan atmosphere. Titan is one of the few places that does have an atmosphere in our solar system. It's about 1.5 times denser than the Earth atmosphere, and it has a lower gravity. As a result of two of those features, it's significantly easier to fly on Titan than it will be here. So Dragonfly itself is about the chassis is about the size of this table, and the whole thing is about the size of a small car. So you're driving a little Fiat around, but that's the Fiat's going to be flying. So after the Fiat is flying through space and we start going into the atmosphere, they at some point jettison that cruise stage. Then they have a little parachute to hopefully slow us down. And this is the absolutely mental part. I'm going to move this. We're going to be a little, sorry, people online. Hopefully you see me. We drop the bottom, we descend down, start the rotors, and we fly. Instead of hitting the planet and then trying to fly, no, we are like, well, that's the whole purpose. We got to fly. So we are going to fly away and hopefully land. To me, that's absolute insanity, and it's really fun, and it keeps me up at night. So it's as you can see here, we're really falling through, and then we just try to fly away, and that was represented in that video as well. So there's some really cool YouTube videos from the science and communications team. I highly recommend looking it up. But as I go into the next part, which is a little bit more detailed, I'm sorry, you can fall asleep now. I'll tell you when to wake up, based off of as I mentioned, you know, you can't have an electrical engineering presentation without some wiggles and waggles and some waveforms. So before getting into that, I want to talk about what is the power architecture of Dragonfly. What am I doing? What is the team that I'm a part of doing? Well, I make PowerPoint slides and I make Excel sheets, but the people I'm working with are brilliant and actually putting this together. So at the heart of all of this, and I say this because I'm very vain and I'm now the battery lead, is we have the battery. We have this 300-pound, very large system. It's about half of a Tesla battery in terms of its capacity, for us to fly out there and really be the core of powering all of our lander loads. So what I call lander load is your communications network, your science instruments, anything that's actually important for us to kind of deal with the actual mission and the science behind it. And then you also are powering your whole rotor drive networks, your electronics box the electronic boxes that will then power the motors and turn the rotors so that you can fly. So as you could probably see, there's 8 rotors and motors on Dragonfly itself for us to be able to fly. It's an octocopter. And those are all supported through the battery itself. Now, you may be thinking this is a big battery and you have a lot of motors and stuff. Well, how the heck are you recharging the battery? I need to recharge my phone about once a day, so while I'm sleeping. In this case, we have an MMRTG, which is a little nuclear reaction happening in kind of the back. So in the trunk of the car, or in the trunk of our Fiat, we have this little nuclear generator that is slowly charging up the battery. So you have that whole network over there, and that takes about 2 weeks to recharge the whole system, and then we fly for about 40 minutes. So it's a really exciting duty cycle where, you know, I don't care for about 2 weeks, and then someone will wake me up and tell me we got to fly. So then I'll get excited. So all of this part you can see here is within the lander itself. So in the rotorcraft, in the maroon, here we go, in this box here, part of the rotor drives is of course outside. And if I didn't mention that it's about 170 degrees Kelvin and everything freezes for most of the part, it's terrifying and exciting to overcome. I apologize, I should have mentioned that. But one of the things with that is just how everything is integrated and how we're trying to think about putting these different pieces together. Additionally, we have a little bit of a small battery called a primary battery, which is a one-time use battery. Secondary batteries seem to be the ones that we recharge. I don't know. I didn't come up with the names. I'm not really a battery person. So please, I will give your complaints to, along with mine, to our battery experts. But we are using a little bit of a boost. So we have kind of like a little turbo so that when we come down, as we've been falling through Titan's atmosphere, we're going to be able to make sure that we have enough energy to land. So for the first about two years of my post Virginia Tech life, I was a member of the Rotor-Tribe electronics team. We're building this, you can see this board here, providing some of the details. We have 4 motors for one of the RDEs, the Rotor-Drive electronics. So you can see kind of all of the cables and harnessing here that will come out, and each of our inverter systems or our motor drive circuits for each motor is here in our ESCs, the electronic speed controller. Along with that, we're using a sensorless 6-step commutation network. Yep, this various details. We have a speed control loop. We have current control loops using 3-phase H bridges. The exciting part that I'll talk about is that we are using silicon carbide MOSFETs. For those who, I know some of the people here work on that. It's the first time silicon carbide will hopefully go to deep space. And it's also the first time that there will be ever active cooling in a deep space environment, because why on earth would you ever think that you need fans or active cooling in space when it's 170 degrees Kelvin outside? Thank you for chuckling. The pun was intended. So additionally, breaking things down a little bit in terms of a cartoon for our circuit architecture, you can see how those rotor drives themselves and those ESCs are connected to the motors, connected to the rotors, and how some of the power is going. So the battery is producing a roughly 72 volt to 105 volt range. So our electronics need to be able to operate over the entirety of that. When we're there, it's great to have that much voltage, but for the most part, we're looking to operate between 90 and 75 based off of the state of charge of our batteries. Additionally, oh, here we go. So 74 is our operating conditions at the moment. Each ESC output is about 3 kilowatts. So if you could imagine, each of these slices is starting to get a little spicy. There's a lot of heat and a lot of current going through there. One of the things, we do have a PCB fabrication facility on site, which is really exciting. So we have a lot of controllability. The thing is, all of our stuff is kind of old. So we went through a whole study trying to just determine how to fabricate 4-ounce copper boards, which I'm sure some of you can just go online, get that very easily, so that we can have that qualified for spaceflight boards themselves. So I mentioned some of these random, or what seem random, comments about things that we've worked on, but I want to highlight that one of the best parts about being a grad student is learning how to learn and be adaptable to go do different things. So again, I did not necessarily know the entirety of a PCB fabrication process, but you know, my boss tells me I have to help support that. And since he pays my paycheck and I have a mortgage, I kind of need to do what he tells me. So you'll learn what you can. So as going on a little bit more into depths, I wanted to mention here, this was quite exciting for us, is integrating silicon carbide devices as our primary switches for the motor drive circuit itself. It's quite exciting to be able to use this technology because it's been integrated into terrestrial applications, electric vehicles, excuse me, for some time. But the other odd part is we're willing to risk that. But for these devices that we're using to make sure that we hold the system off the entire time we're in our cruise stage for about 7.5 years, we want to ensure the highest reliability, so we have silicon devices. To me, it adds a quite interesting dynamic of risk and reward, and how you want to approach some of these design considerations. Kind of moving on, this is just a picture of a circuit board and some of the different features that we have here. This is our breadboard, so it's very kind of messy and spread out. As I mentioned, as we get to a more advanced and more sophisticated flight-like deliverables and assemblies, every piece of mass is accounted for, and we want to make sure that we are as dense and efficient with our space and our mass as we can be. So nothing like this would be allowed, but it's quite nice that we have been able to do this in iterations and steps so that we can get some waveforms. Who doesn't love a waveform? It's and here you can see we were able to spin a motor at 100 RPMs, and we transition spinning the motor up to about 1,000 RPMs. So to us, that was a huge accomplishment and one of our big kind of steps forward as we're trying to ultimately finish our design. I'm gonna kind of move things along a little bit. There's some exciting stuff coming up. So one of the biggest questions, as I kind of mentioned, is one of those slices is expected to carry 45 amps up to 65 amps with no problem, and conduct all of this power and energy inside a small power dense box. So what we found was, at least through simulation, that if we didn't have any type of cooling, we are going to be at approximately 214 degrees Celsius. So I don't know about you, but I don't have any kind of semiconductors that are rated for at least for space that really operate well under those conditions. So how did we want to approach overcoming this and determining what we needed to do? So we have some great thermal engineers, packaging engineers kind of come up and start doing various thermal analyses. They built a very nice ANSYS model for us to conduct these simulations based off of our mechanical designs. So as they were putting things together, we started to think, you know, we're going to be flying outside and we're going to have air inside of Dragonfly. Well, could we use that? So started to think, as we looked at phase change materials and using a passive approach. And then we started having conversations of, you know, this sounds kind of stupid and I wouldn't say stupid. This seems a little far out there, that we're really thinking about putting cooling fans inside of our electronics. but you know, it seems to work. So we decided let's figure it out, and we started trying to find someone who was as silly as we are to make these for us. And we found one company in France. So I got a nice trip to France, have a nice glass of wine afterwards, and we found some cooling fans, and you know, we're going to start testing it out. So we developed a what we called the thermal module for the RDE, which is really a representation. So it's kind of like an experiment as well. We're taking this, we're starting to represent all of our losses throughout the entirety of the system. Our semiconductors, our different types and some of our different magnetic components, whatever power is being dissipated through, we are including as a thermal, we kind of put a Kapton heater or a cartridge heater or something to mimic what the loss is in that area. So we built up a whole board. It should be, oh, okay. This might be in 2 slides. We built up a whole box and a whole board, and we have these unique test conditions and test chambers here. So here's our normal normal thermal chamber. We have our rack, our distribution power rack here. We have a kind of a control board, which there's cabling that we removed just to take the picture, so that we could test everything first inside. And then we have a really cool special chamber called the Titan Pressure Environmental Chamber, which is quite unique because it's not only trying to get to the Titan atmospheric pressure, but it's able to get to certain cryogenic temperatures as well. So we are able to take our box, we're able to put it inside, manage the temperature that they're telling us, and then increase the pressure up to 1.5 atmospheres. And we are then able to, you can see kind of inside with the box, we have various pressure sensors, we have temperature sensors, thermocouples, so that we're monitoring everything. We have like gigabytes of data to monitor how everything would look. So here you can see again some of the simulated results that I wanted to highlight based off of the airflow. So the fans that we selected have certain characteristics where it sounds extremely loud. We bought really cool headsets. They didn't let me buy the Ferrari headsets, but we managed. And as you can kind of see, here's our nice airflow going through. We had to make some modifications, some design changes. And then we built this and tested it. And you can see a lot of the power dissipation going through the entirety. It's just some charts. We do have a paper that was published on it. It was quite fun. And you can see there's me and some of our team members coming together with the actual assembly. That was that TPEC chamber. So you can see I'm not a small person. This thing like sits all the way up here. You could probably put, I would guess, 8 of myselfs in there comfortably before we would start irritating each other. So it's a really fun time trying to get to utilize the skill of learning and the skill of adapting and solving problems to come up with a solution that we are now in the process of developing the first cooling fan that will be used in a deep space environment. Not necessarily counting the ISS, but the ISS could count as well. But for our electronics, this is what we have. So with that, we're going to finally move on. I'm sorry. I know we can talk more about it, but I also want to talk about the moon because we can see it and it's not nearly as far, and doing things there is quite exciting. And there's currently a big, or has been a big push for looking at what's called the Moon to Mars architectures and initiative. Artemis is a big one. Have you heard of Artemis? Okay. Artemis is the twin of Apollo. Apollo was back in the day. I'm a twin, so you gotta keep twin solidarity. So, here are some of the thinking about a power grid on the moon is to me also quite abstract and quite exciting to think about because the challenges are also quite extreme, as we can see here, right? Depending on where you are, you're looking at negative 220 degrees Celsius to 120 degrees Celsius, and that's just outside. There's also there's no atmosphere. You have radiation. The dust is flying all around. The lunar regolith itself is supposedly charged. So now you got dust particles sticking to you. So that's quite exciting. How are you going to get that off? And then you have variations in your solar illumination. If you're on the equator, if you're down towards the poles, your day and night. Does anyone know what the day and night cycle is for the moon, at least at the equator? Yeah, 2 weeks. So a day is 2 weeks and the night's 2 weeks. So it's kind of like you think about every 2 weeks you'll have a half moon and then you see the other part. So that's what you get. And then, as I mentioned before, micrometeoroids and orbital debris. It's way more of a problem on the lunar surface. So from my side, as a power engineer, a power electronics engineer, what are the aspects that we need to think about for a grid on the moon? So I know if any of you are working with Dr. Zhang downstairs, or I guess upstairs, sorry, I'm poorly oriented here, but looking at how are some of these different aspects from a grid infrastructure and integration considered. So the three primary things that we talk about are power generation, energy storage, and power management and distribution. So looking kind of from a breakdown, how are we going to generate our power? Well, there's no wind, so we're going to take out wind turbines, but there's a whole bunch of sun, at least for 2 weeks. So we could put some solar panels up, and if you put them high enough off of the surface, you might get some extra days. If you put them towards the poles of the moon, you might get even more sun. Certain people are looking at then various nuclear sources, some fission surface power, FSP, as well as the smaller radioisotope power, which is kind of like what Dragonfly is utilizing. But again, it's taking 2 weeks for us to recharge Dragonfly. Might not be the most useful for us on the lunar grid itself. Some fun trades are going on right now. We're almost in the time of Tesla and Edison again, but we're gonna put Snoopy next to them with his little astronaut hat and think about, well, what kind of, are we gonna have an AC grid or a DC grid? Are we gonna have a combination of the two? What are the frequencies? What are the voltages? All of those are intertwined with what kind of power conversion that we can have. What are the devices that we can utilize to put on there? As I said, I'm really excited silicon carbide's going on Dragonfly. It's being pushed to very, very high voltages. But at the same time, we're not able to even come close to that because of the radiation impacts. Additionally, we're looking at what are the types of autonomous control. People are talking about power beaming. So shooting a laser from here to over there to then transfer your energy. It's one of the big topics right now. People are also talking about how to do that from a satellite, beam power down. I don't know. I usually just say beam me up, Scotty. So we're just looking at different perspectives here. But there's open challenges and projects and various technological developments that are ongoing right now that and I mentioned this, and I know that there's so much other work going on, especially here and as a graduate student, and it's all of this is interrelated with communications. So RF is huge. How are we taking our sensors, our measurements? How are we looking at our mechanical design, our packaging designs? So leaving the graduate school effort is starting to learn how to piece all these aspects together. And finally, I mean, I have to keep always talking about batteries. At this point, we're looking at energy storage. So fuel cells, battery technologies, specifically low temperature batteries as they get cold. What if they freeze? What if they don't? As mentioned previously, I'm part of what's called the Lunar Surface Innovation Consortium. They're actually having their fall meeting right now in Vegas. So I chose you over Vegas, just pointing that out there. But if you're ever interested, we do have various groups and focus areas. It's free. It's just kind of a bunch of nerds talking to each other once a month about topics that are related to the lunar surface. So in our case, I'm part of the surface power focus area. We have them on in situ resource utilization. So, you know, how are we going to put big construction machines on there and generate semiconductors from the lunar surface? That was a topic. you know, putting a backhoe up there would be iconic if you ask me. But if you want, you can come hang out with us. Every now and then I get to be the MC, so you'll at least get some bad jokes. What's going on right now, as I kind of teased and brought up, there's a couple I think pretty interesting topics. The one representation here is tempo, which, as I said, that there's a push on integrating a lot of these systems. So to me, I'm very biased. Power is at the heart of everything, but you know, how can we also include communications in this? So Tempo is a project that's DC based, and it's trying to transmit power over a kilometer over a cable, but it also includes your communications infrastructure. So here's your solar panel. It looks great. Well, what if you want something down here in this crater? You can use Tempo, which drives down with its cable, and then you can like plug into it, or it can drive off and you can plug something else in. So it's a whole tethered network for you to be able to combine different loads together, different science instruments, to be able to have the energy that you need in the location you need it, even though your solar panel is about 2 kilometers, 1 kilometer away. There's a whole bunch of other programs going on that you can I'm including here over as well. But because I know some of the stuff being done here, I also wanted to mention at least what kind of grid architecture are people interested in? How do you have a flexible and dynamic generation and distribution network based off of what's actually going on and what you're actually able to get? So this is a program out of Ohio State. They're doing some really interesting work combining distributed converters as well as the controls overall. So kind of neat stuff. I don't understand all of it, but I think it's kind of cool. So as I mentioned, one of the open challenges is NASA's Moon to Mars architecture. It's probably the most complete record of where we're trying to go right now. NASA has various mission directorates. So the Space Technology Mission Directorate, STMD, just released a bunch of technology shortfalls. So if you're thinking about different topics, depending on where you are, at least if you're interested in space, here is a list of where there are problems, and we need really creative and smart people to find solutions in overcoming some of this. They do have monetary awards for some of the challenges that they put out. Like some group just won $1 million for figuring things out. And I'm like, man, I'd love $1 million. That'd be great. So I wanted to provide that as a way for, there are resources if you're struggling or if you're thinking about what should I work on. There's a lot of information out there for you to think about. So kind of before going into some of the other aspects and kind of bringing us back from deep space back here, or from the moon back down to Earth, where do I at least see some of our future innovations really coming in? Gallium nitride and silicon carbide devices, again, very biased, but also very excited to see how these technologies will be integrated in various systems overall. Gallium nitride right now is also having a really big push, especially in the satellite industry, that they've really been trying to, they have found great success there. And we are trying to determine, once you go past into deep space, will they be as successful? We're really interested in seeing what are the power distribution architectures that should be considered, right? We're Tesla versus Edison again, but how do we do it in a way that we can utilize the information we have here? Navy ships have been really useful for us to kind of take that architecture and think about how to approach some of these problems. And particularly, we want to keep everyone safe. You know, we have a hospital pretty close by. I'm not saying anything bad, but I'm just saying it's close. So, but if you're going to have some kind of electrical issue while you're in space, well, there might be Mark. That's who you can have to help you. So there's no hospital necessarily. So we want to make sure everything is done in a way that's also responsible and able to protect not only the electrical grid itself, but also the humans that are interacting with it. Material development, as I said, these are the people that can really make the paradigm shifts. If you're able to find materials to really push the envelope in extreme temperatures, radiation tolerance, I'm not even sure what else, but you can really create a lot of impact throughout everything. And personally, I think energy storage, battery technology for space applications has not advanced that much in the last, I don't know, 25 years. We're using lithium ion. It is very useful, but we are limited in terms of the capacity. We are limited in other safety factors. So we need to start thinking about what I think that there's a great opportunity in looking at what technologies are coming up in the future. So why should we even be caring about any of these things here on Earth? What have space programs ever done for any of us? Well, to me, the first is memory foam. It was pretty fun looking up all the different applications that have come out of various NASA and space aerospace industry programs. Memory foam, GPS, which has varying starts. Scratch resistant lenses. I wear contacts, so when I take them out and I put my glasses on, it's quite nice to not have to worry as much. But here you can see some of these far out and thought-provoking questions that the scientists are asking in terms of space exploration, geography, or geology. Was really stretching what we have the capabilities to go do. And now we're able to invent and find new technologies and new solutions. And a lot of that is now able to come back here onto Earth. Here's the Parker Solar Probe, the heat shield, because it gets so close to the sun. That's now being used in the oil and gas industry to help with some of the mining, as well as other various, I believe, energy sector uses as well. So the last thing I kind of want to bring up, because I know we're short on time, and if anybody has any questions, or you can just go home, and it was a beautiful day out. It's probably dark at this point, but technology development and integration can happen at any level. So I know a couple of weeks ago, or probably 2 months ago, one of my coworkers at Reynolds was here talking about more system level things. Well, he's able to influence a lot of this technology development and really push the envelope forward. And it's great to hear from individuals who are so prominent in the field and really visionary in this way. But me and my buddy Jesse, who are hanging out in the lab, well, he had a great idea. And now we're pushing it forward. And we're able to make a contribution ourselves as just kind of individual engineers as well. So it doesn't matter where on the totem pole you are, you're able to make an impact in it, and at any level that you're existing at once you're after grad school. And I want to say that as a graduate student, you really do have a unique opportunity. As we talked about kind of that vertical integration of your project and where you're at, you have a unique opportunity to go into depth on a particular object or particular question and a particular solution that you might not have ever again. So that was something that was first told to me. And looking back, I definitely appreciate what that is, or what that experience had and gave me. But I do want to mention is, while you're going in the weeds, there's a lot more to what the technology you're doing and what the solutions and problems that you're facing are. And maybe this is me on my soapbox for a quick 30 seconds, but I want us just to think about with how everything's going in the world, especially in this region. We want to think like technology is awesome, but we don't need to be dicks to each other. So I think that's a lot of time. I'm also really bad at communicating, which you'll find I can be quite direct sometimes and maybe not as pleasant, but that's when I'm really trying to solve a particular problem. You go find me at the coffee pot later on, and we're able to talk about anything. And to me, the people I work with are way more important and way more fun to get to know than, trying to get the motor to spin. The motor spinning is pretty awesome though too. I would recommend, as someone who's highly involved in IEEE and AIAA as well now a little bit, growing in a professional engagement is a really cool, unique opportunity and provides you ways to also do some community volunteering. So having been a graduate student, I was able to go and do a lot of STEM outreach programs, different community outreach programs. And I have to say that I fully believe that my experiences in those other activities has made me a better engineer. You start to think about solving problems in new perspectives and trying to learn how to communicate what you are doing to different audiences, to be able to share and explain why it's important. So me talking to you today, I get really excited because I can talk all the nerdy words and it's fun. But my mom doesn't know any of the nerdy words. So to make sure she understands how much I care about it, I've been able to learn how to change those those communication skills. And that's particularly by teaching 9-year-olds how to do science experiments. So it's a really, I know that we all get stuck in the weeds, but think about it. If there's a new opportunity that ever comes up, I highly recommend maybe just take one chance and go and volunteer a little bit. So let's bring it all back. What did we talk about today? We talked about some of the challenges that face, particularly power electronics, but all electronics really, for deep space applications because of their environments. Talked about from the mechanical aspect, some of the radiation aspects, constraints from our launch vehicles. Then we went and talked particularly about the Dragonfly mission. Sorry, I talked about ad nauseum. And anyone asleep is now able to wake up. We're closing it out. And we showed a cool little video, and hopefully you started to see that, you can go working from testing semiconductors to building systems for aerospace mission or deep space space exploration missions. And just you learning how to learn as a graduate student is as meaningful as whatever you will produce. And one of the words of wisdom I was given is some of your best work will also be done after grad school. So even though you want to make sure that your advisor is happy with the quality of work, it doesn't necessarily need to be perfect. I say this, sorry. We also talked about some of the future, if there would be a future lunar power grid, what it might look like, what are the challenges putting it on there. And then we wrapped it up with technology developments coming from the aerospace industry down here to the terrestrial world, and also considering what else is going on and how we can make ourselves better engineers. So with that, I got to thank the lab for kind of letting me come and hang out here. Also thank you all for listening to me talk for about 50 minutes. So, I'm happy to answer any questions or hang around or chat. So thank you all very much.
Thanks, Joe. Very, very interesting and informative talk, especially for me, but as someone from the non-electronics community. So very interesting. Thank you. So yeah, we have time for questions. And people online too. You can just
Hi, I have a question.
Yeah, go ahead. Is this online?
Yes, I'm online. Hi, I'm Ishan. It was really good to listen to your talk today. So there was a fundamental question I had about the your presentation. I mean, I got the engineering aspects of it, electronics aspects of it, but I have a very fundamental question. So you mentioned that we are trying to study the how things got here as we are. I mean, humans, the evolution. So I understand that there were right conditions. There was first microorganisms, then came the water on Earth, and then they evolved. Microorganisms evolved into aquatic, then it evolved into land and all, and here we are today. So I mean, the question is that what is the end goal of this? I mean, is it just for purely research purposes? Why we need to? I mean, why do we need to study the origins of human life, so to say, or any life for that sake of matter? Why is it crucial to study that? I mean, is it purely for research purposes, for our curiosity purposes, or is it that we have some tangible goal, key goal, end goal that we're trying to achieve?
I mean, I can give you tangible answer or the philosophical answer. So just to be warned. So the tangible answer is, why do I care? Is because I have a mortgage and I like to do fun things. I mean, let's be real. So the more philosophical reason, which I ask sometimes, is right. This is a $1 billion project. Is it meaningful? Besides whatever inventions and aspects from technology we can utilize for here. So the short explanation is what I learned is in the progress of Earth kind of becoming Earth, Titan is like you take a slice out of that history there, and then Earth continued on, and Titan is still there. So we don't have a good way of understanding or studying a lot of what had happened that hasn't been kind of tampered with or disrupted in some way. So there are a lot of aspects with regards to the physics behind planet formations and just kind of general evolution of a planet that we do not know or understand. And this is one way, and I know a kind of a, in my mind, a cool experiment for us to use and learn more in terms of the growth of a planet formation, and as well as potentially biological life, in terms of kind of fundamental physics applications. So there are various scientific avenues. I am certainly not an expert on that. I'm happy to point you and connect you with the right people if you would like. So hopefully that satiated your question to a basic level. Again, I'm sorry, I like building the stuff.
No, I
I
got it.
don't
Thank
like
you so
asking
much.
the tough questions.
Yes, thank you so much.
Is the Dragonfly gonna fly autonomously, or how does that work?
Yes. So we got a really cool team of people called the mobility team, and they are the biggest pains in my ass because they want to fly this much and they want to make the battery turn into a potential explosive. So no, they are fantastic people, but yes, they have kind of preset types of flights. I don't know, they just renamed all of them, but in my way of demonstrating, one is a helix climb, so to go up into the atmosphere and do some science up there. So that's pretty cool. So you're going to go and all the way back down. One has been a leapfrog, so you're actually starting to go past using demonstrations here. So here's Dragonfly. You are going to go to where you know you want to land. You're going to go over and scout where you want to land the next time, and then come back and land where you now are able to. So they have a predetermined set of flight patterns that they've prescribed, but Dragonfly itself will autonomously determine some of those locations and make those decisions based off of boundary conditions. So like we can't go outside certain temperature ranges. We can't, go outside of certain battery states of charge. We can only fly at certain rates, I think speed wise for stability reasons. We're actually quite slow process. I want to say it's like 100 or 400 hertz is like our kind of control, our main control algorithm. So yeah, but yeah, it is technically an autonomous system, which is terrifying. But it takes a long time to transmit anything. So, by the time you say anything, it could be crashed and blown up by the time you hear anything back. So yeah, so the extended mission is designed for about 40 flights, I believe. So it's supposed to fly, I think it's that if we land, we are successful. That's saying something. Like if that's your bar, you understand how tough the problem is. And then it's like 2 flights, 20 flights, and 40 flights. So there's big sand dunes. So flying over the sand dunes is supposedly one of the biggest challenges. And that'll be quite interesting to see how that's accomplished.
So, talk a lot about like the terrestrial applications, like memory foam and water filtration. But it seems like these power systems themselves are there applications for that, for like systems and other types of autonomous systems?
So I will say it this way: is as a result of Dragonfly, we have found some unique niche cases and have been able to either publish or are going through the IP process with that. That being said, because reliability is our focus, we are using technology that I find, I wouldn't say obsolete, but is certainly heritage to anything done here on Earth. So the challenges that we overcome, like we have to be just such a foundational baseline for everyone else that we unfortunately do not have the luxury of being as creative in some of our ways to um, solve some of the challenges that we would have. But that's a good question. I'd love to. We've come up with some crazy ideas before, like having wireless charging battery stuff that's kind of out there, integrating like your coils to within the battery. But you know, those are the real research questions that we're able to come up with based off of the applications. But for the application itself, we're not really looking at pushing the envelope too much. Mm.
Recognize what's inside so that it's okay if you pump sand through the system.
Oh,
Really sophisticated operations.
so, okay, when we're falling through space or falling through the atmosphere, we open various valves and we inject the atmosphere from there. They've figured it out, but supposedly it's very low in particulate count, so like we don't have dust or sand or anything going on up there, and it's still very cold. And then we almost seal ourselves, so we are not supposed to reopen in case of the problem. Exactly what you're saying is because we could get contamination within the lander itself. So for the most part, it's almost like once we let air in to help pressurize the entire lander, we are then like a sarcophagus. We're hermetically sealing ourselves almost. So we have an external fluid loop even to help with cooling the air inside the lander itself, besides just the fans for what we have. Yeah, correct. Mm-hmm. Yep.
So actually, I had a really quick question. Maybe a little naive, maybe, but kind of nerdy. It's with that slide where you had all the waveforms. I think slide 15 or so. And I noticed something very interesting there. There's a really interesting parallel, I think, coming. Yeah, that slide. That phase change diagram, I think, the one in red, is very, very similar and interesting to a lot of optical materials. And it's a classical pitchfork bifurcation diagram, I think. And I noticed you mentioned phase change materials. So so that kind of indicates that a lot of the materials you're using have a very high degree of nonlinearity, and then you have to deal with this. Right. Okay. Okay. So it doesn't actually play into the material side of things and choice of materials. Okay.
But one of the things, so phase change material is something that we did not choose phase change material in this case because of, but we are integrating it in the batteries now because of they're in the process of right now we're evaluating the energy, the melting temperature.
Okay. Right. Very interesting. Yeah. Okay. Yeah, I'm noticing now it's only current. So, but other questions? Well, if not, let's thank Dr. Kozak again for a very nice talk. And